Suppose the probability that a U.S. resident has traveled to Canada is 0.18, Mexico's 0.09, and to both is 0.04. I don't know what that last sentence is. What is the probability that an American chosen at random has traveled to Canada but not Mexico? So, we know that out of the 18, 4 went to both. So what would we need to do? Yep, so I don't know what just happened there. 0.18 minus 0.04 is 0.14. What is the probability that an American chosen at random has traveled to either Canada or Mexico? What does that imply we need? What's the probability rule for or?
Probability of A plus probability of B minus the probability of, or like minus the intersection.
Yep. So I rewrote it in terms of Mexico and Canada. So we need the probability of Mexico is 0.09 plus probability of Canada is 0.18. And then we need to take off the intersection, which is that 0.04. So when we do that, we get 23.23. Now, I'm doing it this way this time because I did not draw a Venn diagram. We could have drawn a Venn diagram and done all of that, but I just wanted us to be able to just do it mathematically without having to draw it this time. What's the probability that an American chosen at random has not traveled to either country?
Do the complement.
So it's the complement of what? 1 minus the probability of what? Well, it would just be of this, right? Because this is that they've gone to either. This is that they've gone to neither. So 1 minus the probability of M union C. So that would be 1 minus 0.23, which is 0.77. What's the probability that someone who has traveled to Mexico has visited Canada too? What kind of probability is this one? Time to wake up.
My alarm clock.
You need an alarm for 10:30?
I don't know why.
Is it like the wrong 10:30?
I don't know. Sometimes like that's probably like from the weekend or something. I don't know why, but sometimes.
Or
it
from
just
last
says-
week while we were off?
I know it didn't go off yesterday.
Well, did you have it set for just like Wednesday, Thursday, Friday last week while we were off?
I don't
That would
know.
make sense, yeah.
That actually makes sense. I don't know.
I was like, that's my alarm to wake up in the morning. Like, what?
It's mine too. I hate that noise. Every time I hear, I'm like,
Right?
Mine's so loud, I have to wake up and turn it off.
somehow.
Mine's
I
too
never
close
get
to my
mine.
bed, so I can
That's
just.
my thing. I'll like for a week or two, like put it away somewhere in the room so I can just walk over, but it doesn't work because I just walk over and then just walk back to bed.
Yep.
Somehow I can never hear mine. It's right next to me, but like I can hear like my dad's and he's down the hall, like and he doesn't hear his. I like wake up and his, but not mine.
My older sister has this like super annoying one that like it's not even like anything fun or like a song. It's literally just like it's a blaring sound and it just keeps.
I was like my dad. He had that one that was like, bah.
I like the ones
Yeah.
that have the things that it like launches across the room and you have to go find it and put it on the like clock to turn it
I
off.
didn't know that was a thing. That might actually be kind of helpful. I should use that.
I would get so annoyed. Put that thing on.
Especially if it like gets shoved in a corner or something, because the only way to turn it off is by putting that thing back on it.
Yeah.
I guess technically you could just unplug it, but
Yeah.
I was
guess,
about to
but-
say, can't you just like,
you know, shh.
cut off its life
It's
source?
called willpower.
That's the thing. No alarms actually really work because if you want to sleep, you're gonna just end up sleeping at the end of it. So.
Everyone's like, when your first alarm goes off and you're like even awake enough to do that, you should just get up. Like, it's not good to keep snoozing your alarm. And I'm like, I don't really care.
Yeah.
I heard like people use like the 5-second rule. It's like once you get up, you have 5 seconds to like actually like rise up. And I tried that, but every time I get to 5, I just start again like recounting. Like you have to get, or I just count really slow, like 1.
Yeah.
Just like my bed is so comfy, I don't want to get out. Yeah. All right, this probability has a special name. What is it?
A.
They have traveled to Mexico, given that they have visited Canada.
Oh.
So a.
I know what it is. I know what it looks like.
Okay, well, tell me what it looks like.
It has like the probability of the intersection over like, or like the thing that's like this, and then it's like over whatever the second one was.
Yes, the probability of C given M. Or wait, probability that someone who has traveled to Mexico has visited Canada too. Wait, what?
Wouldn't that just be like the both one?
Well, this is what is the probability that someone who has traveled to Mexico has visited Canada too?
Yeah, I think you wrote that right. That's like the probability that they've gone to Canada, given that they've gone to Mexico.
Over the.
Okay, we're gonna go with it. It's what's on my paper. Probability that someone who has traveled to Mexico has visited Canada too. Okay,
This is
yes,
gonna
that
be
does
so
make
bad.
sense.
I know.
They're not usually worded this weird. This is a weird one. All right, so the probability that they've gone to the intersection of both is 0.04. We just need to write it as the whole number. It's going to give us a weird decimal. So 4 out of the probability that they have gone to Mexico, which is 0.09, or we're going to call it 9. And that's going to end up being 0.44. All right, let's try this question again like we had yesterday. Are traveling to Mexico and Canada disjoint events,
Yeah.
also known as mutually exclusive?
Oh,
So.
no, because they haven't overlapped.
Correct. No, because some people have been to both.
So there's always gonna be no if there's overlap, right? Like,
Correct.
Okay.
Now, are traveling to Mexico and Canada independent events?
Yes.
So we need to do it mathematically.
Oh.
Oh, do you have to check that the probability of like the given thing is equal to something?
Yeah, so it'll be, in this case, since we already have this number, I'm going to use this number. So the probability of Canada given Mexico should be equal to the probability of the first thing, which would be the probability of Canada.
Can
Pro-
you do it? Is it always the first one? Or?
Yeah, it's always the first thing. You have to flip them if you want to use the other one. But since I had already found this, I'm just using this. So we said this was 0.44. And the probability of Canada is 0.18. Those are not equal, so not independent. Therefore. I just write it to make it shorter. Okay. In its monthly report, the local animal shelter states that it currently has 24 dogs and 18 cats available for adoption. 8 of the dogs and 6 of the cats are male. So I would recommend, if you have something like this, that you do a little table to keep things straight. So I'm gonna do male, female, and then we'll have dogs and cats. So 8 male dogs and 6 male cats. I know that in total there are 24 dogs, so 24 minus 8 is 16, so there's 16 female dogs, and then 18 minus 6 would be, 12 female cats. And there's a total of 42 animals. Just in case we need that for anything. I don't know if we will or not, but we could. Alright, so we don't have probabilities. All we have are numbers right now, so we have to be mindful of that. What is the probability of randomly selecting a male pet given that it is a cat? So, what kind of probability is this one? Male, given that it's cat.
The A and B one? Like P equals A and wait, no, P like parentheses A and B?
No, this would
Okay.
be a conditional one. So this is going to be the probability of male given cat, which is going to be the probability of male intersected with cat over the probability of cat. So remember, for independent, it's the probability that's equal to the probability of the first thing. When we're doing conditional, it's over the probability of the second thing. So they're opposites, just for memorizing purposes. So male cats, we need to figure out how many total, or like what the probability is of a male cat out of the total number of animals. So that's going to be 6 out of 42 over the probability of a cat is 18 out of 42. So that's going to end up giving me 6 over 18 because keep, change, flip with the fractions. So 1 over 3 or 0.3 repeating for that probability.
So what's the difference between like that one and then like D for the last one? Like where we just like we didn't do like the one over the other. Is it just did we do the same thing? It's just we already had
We
that
did.
number?
I just didn't write them separate because these ones gave us probabilities already. This is finding the probability.
Okay.
So like technically I could have just gone straight to 6 over 18 because I knew that the stuff was going to cancel, but I'm doing it to show you that like technically we need to make them probabilities first
Okay.
before we do that. Like on the next one I'll probably, because it's the same type of problem, I'll probably just go straight to the number over because the fractions are going to cancel.
Okay.
So what's the probability of randomly selecting a cat given that it's female? So this one's a little different in obviously what it's asking. So randomly selecting a cat given that it's female is going to be the probability of cat given female, which is the probability of the intersection of the two over the probability of a female. So cat intersected with female is 12. Technically 12 out of 42, but since I know the fractions are going to cancel, I'm just going to write it as 12. Over the probability of female, there are 28 females. So 12 out of 28, which gives us 0.43. So then, what's the probability of randomly selecting a female pet given that it's a dog?
Would this just be like it'd be female over D?
So female given dog. So the probability of the intersection of those two things over the probability of dog. So what's the probability of female intersected with dog? Or like the number.
16 over 24? Oh wait.
Well, this number, the probability of dog is going to be 24, yes.
Okay.
So, yes, technically. Just a little bit of a step ahead. So, 16 is the intersection, and then 24 is the probability of dogs. That's how many dogs there are out of the 42. So, that is going to give us 0.67. So, are species and sex of the animals independent? So I would choose basically one of these things that we have up here. Probably easy one would be just to use this last one. I mean, it really doesn't matter, but let's just use the last one. So probability of female is equal to the probability of female given dog. So I've already found female given dog is 0.67. Probability of female, how would I find that?
It'd be like all the females over 42.
Yep.
Like 28 over 42.
Yep, so 28 over 42, which comes out to be 0.67 also. So 0.67 equals 0.67. So in this case, they are the same, so they are independent. So it's basically telling us that 67% of all animals are female, and then 67% of all dogs are female, which is why they are independent. All right, the question, do you smoke, was asked of a random sample of 100 people. Results are shown in the table below. Suppose we select one of the people at random. What is the probability that a person smokes?
31 out of 100.
Yep, 31 out of 100, which, nice, easy, 0.31 for the decimal. What about the probability that they smoke given that they're male?
19 out of 31? Wait.
So this would be the probability that they smoke intersected with male over the probability that they are a male. So how many smoke and are male? 19, and then how many are male?
60.
Yep. So then that's going to be 0.317. So then, is smoking and gender independent? Explain. So this would be, we would use this probability of smoking given male would be equal to the probability that they smoke, which this is 0.31 would be equal to 0.317. So this one's kind of a weird one that you could kind of argue either way. But that would technically round to 0.32. So I think the book would probably technically say these are not independent because they're not exactly the same. But if you were to say that they're independent because those numbers are super, super close, I would probably give it to you. But technically speaking, these are not independent because these are not equal. All right, you're going to have to write kind of small for number 9 because since for some reason I decided that cramming 9 and 10 on a page together was a good idea, we're going to do a little diagram over here and then we'll do the math on this side over here. So hopefully you have enough space, but just don't write too large. All right, so we have a manufacturing firm orders computer chips from 3 different companies, 10% from company A, 20% from company B, and 70% from company C. Some of the chips that are ordered are defective. 4% from company A, 2% from B, and 0.5% from C are defective. If a computer chip is selected at random and found to be defective, what is the probability that it came from company B? So, I'm going to make a little like tree chart thing where the first branch that's coming is each company and how many chips that they're producing. So I'm going to have A, B, and C each on a branch. So I'm trying not to make these super, super large here so that I have room. So I've got A, B, and C. So A makes 10%, so I'm going to say 0.1. B is 20, so 0.2. And then C is 70, so 0.7. And then just to see it, I'm going to try to use a different color here. So then each of these is going to have a branch off of them, or like, well, I say a branch, 2 branches off that are going to tell us information about that. So, A is defective. Let's do this. Hold on. All right. I'm going to do this. Defective. I'm just going to put G for good. Defective and good. Try to zoom this in a little bit. All right. So, company A has 4% that are defective. So, that's 0.04. That means that good would be 0.96. So 96% are good. B has 2% that are defective, so that's going to be 0.02, meaning that 0.98 are good. And then C is, it's 0.5%, which is 0.005. And then 0.995. You tracking so far on setting this up? All right, zoom it back out because I need to go over here. All right, so they want us to find the probability that, if a computer chip is selected at random and found to be defective, what is the probability that it came from B? So this is going to be the probability of B given that it's defective. So this is going to be the probability of B intersected with defective over the probability that it is defective. Probably writing too big, but I think it'll be okay. All right, so this one's very different in how we set this one up comparatively to the other ones. So B and defective. So that's just going to be 0.2 times 0.02 for that part, because that's going to multiply and give us the defective from B. So the top is going to be 0.2 times 0.02.
I thought we divided it by the first one, but it was like.
No, we always divide by the second one.
um,
Independent is the first one. The first one equal to the conditional. So they're opposites. Independent is first and conditional is second.
Okay.
Over. Now, this is the probability of defective. So you can't just say, oh, well, defective is 0.04, 0.02, and 0.005. We have to know how many of each companies are defective, basically. So this is going to be 0.1 times 0.04 plus 0.2 times 0.02 plus 0.7 times 0.005 should have, oh well, I have room over here actually, can slide it over. So when we do this, this ends up giving us 0.004 on top over 0.0115 for a total of 0.348. So basically, there's a 34.8% chance that if it's defective, it's from company B. So those ones are obviously a little more involved, I would say. But not too bad. It's just really figuring out exactly what they're asking for. All right, number 10. So again, part A, you might want to write, well, the little diagram you might want to write kind of small just to make sure you have room. B's like one line, so there should be plenty of room, but anyways. Suppose that 23% of adults smoke cigarettes. It's known that 57% of smokers and 13% of non-smokers develop a certain lung condition by age 60. Explain how these statistics indicate that lung condition and smoking are not independent. So I'm going to probably just use S for smoking and N for non-smoking since I'm trying to make this a tiny little diagram here. But this one's just going to have two things off of it. So I'm just going to do S and NS for smoking and non-smoking. So 23% smoke. So 0.23, meaning 0.77 don't smoke. And then we're looking at if they develop a lung condition or not. So off of here, I'm going to have basically, I'm going to say LC or NLC for no lung condition off of both of these. Just very tiny area. Lung condition, no lung condition. I don't know if y'all can read that. It's so tiny. All right, so lung condition for those that smoke is 57%, so that's 0.57. That means that no condition would be 0.43. And then for non-smokers, 13%, so 0.13, and then 0.87 for the other. All right, so the way that we're going to set up this one to check for independence is a little different in how, like, the setup of it, I should say, is the same, but where we're going to get the numbers from just looks a little different. Like, we don't really have to do any math for this one. So we're going to say that the probability of smoking, because that's the number that they gave us, is equal to the probability of smoking given that they have a lung condition. So the probability of smoking is 0.23. The probability that they smoke, given that they have a lung condition, is 0.57. So these are not equal and thus not independent. And the other thing that we can say is we would expect the same percent of people to have a lung condition in both categories if independent. Because that would imply that if they, no matter if you smoked or not, you would still get the lung condition. Would be how to show independence on that. So then what's the probability that a randomly selected 60-year-old has this lung condition? So lung condition, it doesn't specify if they're a smoker or non-smoker. So there's two ways that they can have this condition. They can either be a smoker or a non-smoker. So we'll have these numbers and we'll multiply them 0.23 times 0.57 plus 0.77 times 0.13. And that's going to give you 0.2312. Alright, let's see if y'all can figure out how to set this one up. What's the probability that someone with a lung condition was a smoker?
Probability of LC, or like, would it be the, like, given thing?
Yeah. So probability that they have a lung condition, or wait, that someone with a lung condition was a smoker. So basically, so this one's kind of like that one we had earlier where they've reversed the wording. So it's saying that they already had a lung condition.
So, smoker given lung condition.
Yep. So we're just going to also show that this number up here that we wrote down is actually from down here. So what do I, like how would you get this mathematically?
The probability of the intersection between smoker and lung condition over the probability of smoker.
The second thing listed.
Lung condition.
Yep. So smoker and lung condition is 0.23 times 0.57. Over the probability of lung condition we just found in the previous problem. So 0.2312. So more or less those things cancel each other. We technically get 0.567, which rounds to 0.57, which is that number that we had up there already. All right. Questions, comments, concerns?
Well, I wonder, so in problem, or in 8 and then part B, so was the reason that we used,
You said 8B?
I just wrote it, that's why I was confusing myself, because for
Oh.
I wrote probability of smoker underneath, and I was like, okay, that makes more sense.